Hi everyone. Welcome to this first lecture in the unit on systems dynamics. And in this brief lecture, we're going to introduce systems to say what are systems, how do they operate, what are some of their components before moving into more details about systems. So first of all, what is a system? What do you think a system is? Pause the video and think a little bit about what you think a system is. Welcome back. This is a way that we can think of our food system. So our global food system is a system. It's incredibly complex. There's a lot of components. And we can think of systems at a lot of different levels. We can think of our food system as a function of employment, renewable energy, as we see in the top right portion of this picture, food culture, food security toward the bottom, greenhouse gas emissions and wastes. And we can also look at it from the perspective of processing, production, transport between processing and production. So it's pretty complex, right? We could also look at a food system like this. These are linkages, a little more detail about how a food system operates. So you can see there's inputs, there's energy, there's a supply, there's the health system, there's the social system there on the bottom, there's the political system. We've got biological system with climate change and land use there on the left. And we start seeing that all of these pieces, what we'll start to call variables later, are intricately linked to one another. And we're going to get into that in a moment. But notice how there are arrows between all of these different components of this larger food system, denoting that they're all linked together, if not explicitly, implicitly. Here's an incredibly detailed food system map. So as you can see, we've looked at this food system now from three different perspectives, either sort of a simple food system map in that first picture, a little bit more complicated in that second picture, and now very incredibly complicated in this third one. And I love this because this actually is a great example of how sometimes taking systems too far when you're communicating to the public can undermine sort of your goal about teaching some of these interactions. So we're going to learn today that thinking through systems, not only is it important to have incredibly complicated and complex relationships, but also removing the extent to which you can certain variables so you don't get sort of an unreadable situation like this. Not that this isn't the food system, it's absolutely the food system. But sometimes working within this, a model might be kind of difficult to operate with. But still, we can see that once we expand more broadly and look at more variables and more things, the food system can become incredibly complex. So I'm going to put a pin in that because I think it's important in a moment when we talk about drawing a boundary around the system that we're going to be looking at. So what is a system? Everything's a system. Your digestive system is a system, right? It has to do with your esophagus, your stomach, your intestines, right? This is your digestive system that is closely linked to the acids your body is creating, the muscular movements, and it's a system of inputs. A football team is a system, right? You've got your halfbacks, you've got your goalies, you've got so many different pieces that are moving in different speeds and different rates. You've got a manager, you've got a stadium, you've got a pitch, and so many different things that are operating together. And if we draw it out, as we will in a moment, you'll see arrows going to different pieces and components of that system. The university, a school, is a system. A city, the global economy, clearly Earth. This lecture is a system, right? Because I am one piece of it that is delivering through this little remote control to change the slides, a system that is then going into my computer that is being launched into the ethos, wherever YouTube operates, in order to put this onto Minerva so that you, a system of students in a certain class, right, a module, are able to watch this, right? So this lecture even is quite a part of a quite complicated interaction of a system. Systems are actually embedded in traditional jargon. This isn't something that just academics like to talk about, right? We say the rich get rich and the poor get poorer. Well, how does this happen? The wealthy own assets. Those assets return returns through interest rates and capital gains to those wealthy people, which increases the stock, which we'll get into, of their assets, which then are able to generate more returns. The poor have a basic stock of income that they can just flow away from, and you're hearing stock and flow, so if you're paying attention, you're a little ahead of me in the lectures, but good job hearing that. The stock of a poor person's income just gets depleted by the flow of expenses, and therefore, since they don't have these returns coming in, they're getting poorer, right? So just the rich get rich and the poor get poorer can be thought of in terms of these systems dynamics, which, again, I'm getting slightly ahead of myself, but stocks, flows, arrows, relationships, variables, these complex dynamics that are just built into something we hear every day that we talk about. Same thing with don't put all your eggs in one basket. What does that mean? Well, a basket might be your opportunities. Eggs are going to be all your chances for opportunities. Don't put all your effort into this class because then you're going to fail on a different class, right? So diversifying and effort and output, these are all looking at systems again. So again, just something we hear in everyday language is a piece of a system we could think about if we wanted to. So the whole point of this is that everything is incredibly complicated and interacts with everything else on Earth. These things are incredibly complicated and things don't exist in a vacuum. And from an ecological economics perspective, that's really important, right? That's one of the big takeaways of ecological economics and why we look at these supply and demand models critically, why we look at human behavior critically, why we look at the social system as embedded the economy as embedded in the social system, as embedded in the environment, right? We look at these because we, as ecological economists, think that these things are incredibly complicated and these things don't exist alone. Systems are really important for ecological economists. Going real quick back to this food system map, we can look at these relationships really closely. So on this piece that I've highlighted here, we've got this biological system, we've got land use and climate change and fertilizers and types of things there. You can see that this arrow then feeds into where we see agriculture on that top where that cow is, and that agriculture is fed by energy, sunlight, which is also leading then into the economic system. Also, if we look on the bottom at supply, which is a function of the health system and the political system, is driving into that biological system. So all of a sudden we can see if we look at one piece, it is related to everything else. And that means changing any one of those pieces is going to change that biological system. If we have a small change in our political system, since that eventually feeds into our biological system, we need to know how much will that change affect our biological system. And this is what Donella Meadows called leverage points, right? She has two papers that you should have read prior to this lecture, but the short one that she has is places to intervene in a system. And she has these 9 places to intervene within a system, and she says in increasing order of effectiveness. So she basically says numbers, subsidies, taxes, standards. That's going to be the least effective intervention in a system. So when we think about addressing climate change, Donella Meadows, she says from a system standpoint, adding a tax is going to be a very low effectiveness for intervention in a system. But these things are the standard ones, probably because they're most politically feasible, but they've got this shallow leverage for changing the system. Things on the bottom are what we'll call deeper innovations. They have this strong leverage for changing systems. As you can see, the goals and the ontological disposition of that system, changing those really have a huge leverage for being able to address some problems. So think about changing the goals of capitalist accumulation, for example, is probably going to have a much bigger impact on the climate, for example, than a tax on emissions, right? And that sort of makes sense from what we've been learning in ecological economics. But also more generally, it sort of makes sense that if you change the goal of the system, that's going to be a really deep foundational leverage point for intervention in that system. So again, when we go back to this food system map, we can see that a small change in a political system might have an output in climate change or in the land use, but what is the extent of that? We don't necessarily know. If the political system changes one actor, which would be a number, it might not have a huge impact. If the political system changes from top-down autocratic to fully democratic, environmentally focused, that's going to be a different change in the later part of that system because of that deeper intervention, right? And every one of the variables as part of this food system map are going to be function at different levels of leverage based upon how we're making those small manipulations. So this is just a fabulous paper. It's one of my favorites of all time. I talk about it all the time. So familiarize yourself with this. Be comfortable with what Donella Meadows is talking about in this, because this is something that will continue to come up in your ecological economics training. So the history of systems thinking actually isn't necessarily in environmentalism as you might think from just the papers that you read for this lecture, right? It was created by Jay Forrester. He was working in the middle part of the last century with managers at General Electric, and during the 50s and 60s, General Electric essentially went to Mr. Forrester and said, we want you to understand our complex production processes in order that we can basically put some efficiencies into our system, right? So General Electric might have a production plant where they're creating light bulbs. They're also having a production plant where they're creating MRI machines. General Electric was producing a lot of things, so they had a very complex system. They hired Jay Forrester to deal with and map out some of these managerial some of these systems, so that managers could get in and see where are the leverage points for making small tweaks that have big impact on efficiency. But then in 1971, the Club of Rome, which is a group of intellectuals and academics and thinkers, invited Forrester to develop, based on his work at General Electric, this system dynamic model of the entire world. The first was called World 1, and the second one was called World 2. These incredibly complex models that modeled out what the world looks like and how it operates. And then the Club of Rome commissioned later one of Forrester's PhD students to carry out this extended study, and his name was Dennis Meadows. And Dennis Meadows, as you can imagine, was married to Donella Meadows, who wrote the paper that we just discussed. So in 71, Dennis Meadows and Donella Meadows and several other people published this book called Limits to Growth, which we'll discuss later, and we'll discuss in the seminar, based on a third iteration of that world model. And essentially what Limits to Growth did was say, by looking at this complex system that we built within the World 3 model, we see that population growth and increasing consumption is leading to crashes in our global ecosystem's ability to continue to create food and goods for us to be able to consume. So systems thinking really can be thought of as, rather than thinking linearly, thinking in terms of complex systems. So this idea of linearity, that things operate more in a vacuum, versus these intricate loops that are connected to other intricate loops that are connected to other intricate loops of inputs and outputs and all these types of things. Instead of thinking linearly, like if I walk, then my legs move, and then I get to the next point, right? When my legs move, I'm consuming calories. When I walk, I make an indentation in the carpet that might kill a spider. That was a very simple explanation or an example. But changing from thinking linearly to this complicated network of cause and effect. So thinking beyond the behavior of what's going on toward the structure of what's going on and underlying some of these things. So instead of looking at an economic recession, we can look at what happens to employment, what happens to interest rate, what happens to demand. Is there a virus kind of hooked up in all of this, rather than just saying, are we having a recession? We can look at all of these things, the structure of what's going on in the world. Instead of carbon emissions, we can look at what are the emissions laws that we have? What is the frequency with which people drive? What is the proximity to individuals and their places of work? Again, that structure of a system versus, do we have carbon emissions? Yes, we do. Well, let's look at the laws. Let's look at how frequently people drive and how close they are to work to build out a structural, more complicated understanding of what's happening with emissions. Oil prices rise, great. Well, what about the power of cartels in producing oil? What about the demand based on driving frequency and work proximity, right? What about alternatives to oil? Are there green alternatives, wood, solar, hydro, all these different things that we can see as a system for our energy use? And we've got a virus outbreak, right? What is that doing as a function of travel? Are people traveling? So rather than looking at, yes, we have a pandemic right now, are people traveling a lot? What is the weather? When people go outside, the outbreak seems to subside. What is the age of individuals across geographies? Are people immune based on certain other things? How contagious is this? Right? So we know over the last couple of years, there have been a lot of really critically important systems models that have looked at this virus outbreak. Right, and we can similarly look at fisheries. What's going on in fisheries, rather than just looking at, is there depletion in a fishery, like what are the demand for fish and all these other complicated structural components of that system. So when we think about a system, we want to think of the components of a system. And this is hearkening back to when I said put a pin in it a little earlier. When we think about a system, we've got the system boundary, right? What's inside the system? What's outside of the system? And ultimately, if you're kind of keen and paying attention, everything is ultimately within the system of Earth, right? So we can't really piece any of it apart, right? When we look at the broad macro, everything is part of this system. But we're able to look down at a system and say, okay, we're going to look within this boundary, right? So I don't need to think about the rainfall in Madagascar today when I'm thinking about the system of my laptop in this lecture, right? So the boundary might be this lecture, and that's where I'm going to draw that boundary. Then we've got elements of a system, right? There might not be too many. Remember when I said before, we could have 100, but it might be easier if we can look at maybe 6 of the really big ones to really understand what's going on. That doesn't mean that all those other elements aren't really important, likely, but when we look at a system, it's best to think about it as the most simple to figure out what's going on and then build up from there. So we've got a few elements going on in this system within the boundaries of the system. Then we've got links between these elements, right? And these links are the manner in which these elements are related. And we'll get into that in a little bit in just a moment. And then finally, we've got these exogenous elements. And these are the things that are outside of the boundary of that system. So let's look really briefly at some of these. The boundary, the boundary helps us focus on the topic without becoming too distracted by outside factors. Like I said, everything ultimately is connected, but we can't look at the entire world all the time when we want to look at a smaller problem, right? So the boundary is, within that is the stuff we care about, and this outside of it is everything else, right? And we set up this boundary in order to really be able to focus on what we think is really important for the system we're looking at. These main elements could be anything. It could be key actors in the system. It could be institutions. It could be policies. It could be environmental phenomena. Sometimes we'll be looking at stocks of populations of animals, stocks of carbon dioxide. These elements are just key actors, institutions, policies, these things that we're really interested, parts of this system. So modeling these systems, which we'll get into in the next part of this unit, is about getting as close to the essential factors as possible, right? We kind of use this 80-20 rule, whereas if we think we can get 80% of the system operating correctly by only looking at 20% of the elements, that makes it a lot easier for us to model and think through this system. So we hope that we've got some big elemental players that allow us to keep our model simple as we build and analyze it. Okay, so with these elements, if the issue is land degradation, then cattle owners are as important as cattle. Right? Sorry, my light just went off. It thinks I'm not in here. Sorry about this. This is embarrassing. Come on. There we go. I'm back. Sorry. This remote teaching is always fun. So right, if our system that we're looking at as our issue is land degradation, cattle owners are as important as cattle within this situation. So we can't just have cattle because we need to have cattle owners. What is driving cattle owners to do what they're doing? Other times we might say cattle aren't needed. Cattle owners are all we need to understand because that's the more important element. So understanding your system and what's important and what can be left out is really critical. And again, like if our issue is income inequality, then the profit motive of capitalist economies is as important as money, right? So that could be true. Other times you might say, no, the profit motive is absolutely critical. We don't need to worry about money, right? So usually we can say that these two similar and distinct things both need to be elements. Other times we might say one is more important than the other. So again, it's about getting as close to these essential factors as we possibly can. And the links between these elements, we want these connections to be direct, strong, nameable, and describable, right? What is the link between one piece of an element and another one? And if it is an element is land degradation and the other element is cattle running, what is that link? And we can look at frequency of grazing, hours of grazing during the day. Those are links that are going to link these two elements directly, strongly, nameably, and describably. And we can describe it by saying when the owner of the cattle opens up the gate, the cattle go out and graze, and they cause that land degradation. And when they open the gate in the evening and they go back into their pens to sleep, that ends, right? But that link then is the relationship between cattle and overgrazing, right? So those connections are direct, strong, nameable, and describable. Very much important to understand what those links look like. Now, usually these links only go in one direction. That doesn't mean there aren't, as you can see on the left here, multi-directional links between some elements, right? With one element having an arrow that goes one way and the other element having an arrow that goes the other way. But if there's another directionality, it's a different link and it needs to be described. So we don't tend to have arrows with two arrows with an arrow on both sides. We have our links most often going only in one direction because, again, if there's a different direction, it's a different link. It's going to have a different proportionality. It's obviously a different element beginning and a different element ending, and therefore that link is slightly different, even though it might be between the same two elements. So elements can be linked directly, and that's sort of the whole purpose of the systems analysis. And complexity, they can be linked indirectly. So we can see in this example that this top element is linked indirectly to that bottom element. It's linked through that middle element, right? Assuming that those other ones are also operating, right? So elements don't necessarily need to be directly linked to be indirectly linked. And then these exogenous factors are these external game changers, right? What's going on outside of the system that's also causing that? To go back to that example of cattle and land degradation, maybe there's something outside of this system that we don't understand. Let's see, maybe in the evenings kids come through and like to party in the field, and that's not something we know about or really can do anything about without different laws that are outside of this system, right? So these are external game changers. Systems can't do anything about this exogeneity, but are affected, right? Maybe more importantly, because you could probably stop teenagers from partying. Every year there was a windstorm that sweeps boulders across the land and kind of crushes the land. There's nothing you can do about that, but those fields are affected, right? So systems can't do anything about this exogeneity, but need to understand it because it's critically important. So like, what are some new international treaties, for example? What is the role of national policies? What is the role of economic crises, pandemics, what's happening that we can't predict, right? These are external game changers that we can't do anything about. So we can ignore them in general, but awareness of those potential exogenous factors is very, very important. We should know that there are things out there and then just not worry about them for our particular model. But understanding what they could be is pretty important. Okay, so I've got an activity for you. Go ahead and pick a system that you're interested in. It can be anything. It can be the university, it can be the climate, it can be a farm, it can also be your decision to purchase a new guitar. It can be anything you want. Define the boundary, the elements, the linkages, and the exogenous factors. Draw it out and post it on Padlet 1 in Minerva. And this system can be drawn on a piece of paper with pencil, and you take a picture of it and throw it on Padlet. You can draw it out in any sort of a computer program that you prefer. But either way, draw a system that you want and post it into the Padlet on Minerva. Thanks so much, and I hope this was a nice introduction to systems. In the later lectures, we'll get into a little bit more detail about how systems operate and what those linkages look like.